In a 27-kilometer-long tunnel buried deep underground at the CERN laboratory, the 7-story-high ATLAS detector is designed to enable scientists to study the conditions of the early universe. In this episode, we will see how ATLAS works. The detector consists of many components. These are needed to measure the different types of particles produced in the collision, which then pass through ATLAS. The intersections measure the tracks of charged particles, which are bent by the magnetic field of a thin superconducting solenoidal magnet. Outside of all of these are two calorimeter devices measuring the energies of particles. Finally, the muon spectrometer measures the tracks of muons, which are bent in the field of the superconducting toroidal magnets. Here is how ATLAS detects different types of particles. An electron will plow through the inner detector, leaving a track behind before finally stopping in the electromagnetic calorimeter. A photon behaves in a similar way but leaves no track. A proton leaves a track and interacts primarily in the hadronic calorimeter. A neutron behaves in a similar way but leaves no track. A muon passes all the way through ATLAS, leaving tracks behind. Finally, a neutrino passes through ATLAS without being detected at all. Billions of subatomic particles called protons advance towards each other from opposite directions at almost the speed of light. As two protons collide, hundreds of new particles are formed from the energy of the collision. These collisions occur 1 billion times a second. At the center of ATLAS, the inner detector, which measures the tracks of charged particles, is composed of the transition radiation tracker, the semiconductor tracker, and then further in, the pixel detector. Now zoom into the semiconductor tracker and pixel detector. These are made up of several thousand tiny modules to detect particles produced in the collision. The semiconductor tracker and the pixel detector work in a similar way. Let's now see how the pixel detector works by looking at one of these electronic modules in more detail. There's a thin top layer of silicon connected to a lower layer of electronics through a large array of solder spheres. To see what happens in the silicon when a charged particle punches through, zoom to the scale of the silicon molecules. As a charged particle goes through, it liberates electrons. These electrons move to the bottom of the strip, creating an electric current through one or more spheres. By seeing which spheres had a signal, we can tell where the original particle went. The signal is converted into binary numbers, which are stored and analyzed by the scientists. Look now at the transition radiation tracker outside the silicon detectors. This device can distinguish between different types of particles. It's made of a large number of tubes filled with gas. Whenever a charged particle passes through the material between the tubes, photons are produced. Let's see the difference between pions and electrons. A pion entering the tube ionizes the gas and is accompanied by the radiated photons. The photons interact with the molecules in the gas, freeing more electrons, which move towards a gold wire at the center of the tube where they are measured. If the initial particle is an electron, far more photons are radiated than with the pion. This means that more negative charge is measured on the wire. This measurement allows the ATLAS detector to distinguish between different types of particles. Using the inner detector, ATLAS can measure the paths of charged particles which are bent by the magnetic field. From these paths, it is possible to calculate the momentum of charged particles. ATLAS also has detectors which measure the energies of both charged and neutral particles. These are called calorimeters. The ATLAS electromagnetic calorimeter is used mainly to measure the energies of electrons and photons. Its accordion-shaped structure consists of many layers of lead and stainless steel. The particle absorbers. Between them is liquid argon, cooled to -185 degrees Celsius. Immersed in the liquid argon is a copper grid, which acts as an electrode used to make measurements of particles which pass through. We can now follow a high-energy electron through the electromagnetic calorimeter. Whenever the electron meets the absorbers, it interacts with the material and produces a shower of low-energy electrons, positrons, and photons. The high-energy electron will pass through several layers of absorbers, creating a large shower before it eventually stops. The shower of low-energy particles passes into the liquid argon and ionizes the atoms, creating more negatively charged electrons and positively charged ions. The negative charge is attracted towards the copper electrodes, where it's measured. From the amount of charge deposited on the electrodes along its path, it is possible to measure the energy possessed by the original electron or photon when it entered the electromagnetic calorimeter. Now we see the large outer calorimeter, the hadronic calorimeter. This device is used to measure the energies of a set of particles called hadrons that includes neutrons, protons, and mesons. It is a large array of interleaved steel and scintillator sheets called tiles. A scintillator is a material which radiates light when exposed to a charged particle. When a high-energy hadron, like a proton, passes through the steel, it interacts with the atomic nuclei. These nuclear reactions lead to the production of more particles, which initiate further interactions, leading to a shower of particles. The particle shower which is produced enters the scintillator, causing it to radiate light. Long fibers then carry the light to devices where the light intensity from many tiles is measured and converted into an electric current. Using the intensity of light, it's possible to measure the energy possessed by the high-energy hadron which entered the hadronic calorimeter. Particles known as muons can penetrate through the calorimeters and reach the outermost part of ATLAS, known as the muon spectrometer. The muon chambers in ATLAS cover a surface of several football fields. One segment of the muon chamber contains many small tubes filled with gas. As a muon passes through these tubes, it leaves a trail of electrically charged ions and electrons which drift to the sides and center of the tube. The circles show the starting point of this drifting in each tube. By measuring the time it takes for these charges to drift from the starting point, it is possible to determine the position of the muon as it passed through. From particle collisions like this, ATLAS scientists can explore the fundamental processes that rule all matter in the current universe and in the very early universe.